Hello, everyone. My name is Bodan Vilkovsky, and I'm currently a master's student at the Faculty for Electrical Engineering and Information Technologies in Skopje. And I'm currently doing my master's in the field of metrology and quality management. I will be doing a video presentation on the subject of data acquisition techniques using LabVIEW. This presentation is funded by the Erasmus Plus Key Action 203 Strategic Partnerships for Higher Education, and it is part of the project titled Innovative Teaching Approaches in Development of Software-Designed Instrumentation and its Application in Real-Time Systems. So we're going to jump right into the presentation here. Okay, so on this first slide, we have the outline or the contents of this presentation and all the topics we're going to be covering in it. Before I begin, I want to point out that this presentation is intended for students that already have some knowledge in LabVIEW programming and have already covered the basic principles and some simple architectures used in LabVIEW, as that is the programming language that we're going to be using for this presentation, as the title suggests. So first we'll give a brief overview of what data acquisition systems are and what they are comprised of. And next we're going to cover the NI DAQ MX virtual instruments. That is an instrumentation palette for LabVIEW, which is actually a library that allows communication between LabVIEW and the National Instruments hardware. Then we're going to get into the heart of the presentation, which is the actual acquisition techniques. So we'll be covering analog input, analog output, as well as digital input and output acquisition techniques. So the first part of this presentation will serve as an introductory part, and I will give a brief introduction and overview on what data acquisition is and what data acquisition systems represent and are made up of. So what is data acquisition? Data acquisition, or DAQ for short, is the process of automatic collection of data from sensors, instruments, and devices, whether it be in a factory, in the laboratory, or in the field. So, and the purpose of any DAQ system is to measure some physical phenomenon, such as light, temperature, pressure, or sound. And any data acquisition system is made up of or includes these following building blocks. So we have the sensor, which is used to acquire some sort of signal, um, and then this sensor relays this input information to some sort of data acquisition hardware. Uh, most of the time we need to use some sort of signal conditioning in the process of relaying this information from the sensor to the data acquisition hardware. And then this data acquisition hardware transfers the measured data to the DAQ software, which is most often located on a computer via some sort of interface or bus. So signal acquisition, as I said, is the process of converting physical phenomenon into data the computer can use. And every measurement starts with using a sensor, also called transducers, um, in order to convert the physical phenomenon into an electrical signal that data acquisition system can measure. Sensors most often generate electrical signals to measure parameters such as temperature, force, position, sound, or light. Some common types of sensors are listed in the table on this slide. We have to take into account that different sensors have different requirements for converting a physical phenomenon into a measurable signal. For example, a resistance temperature detector needs an excitation current to measure the temperature, whereas a thermocouple does not need excitation current, but it does need cold junction compensation. Strain gauges, on the other hand, use a configuration of resistors called a Wheatstone bridge to measure the strain. And before you set up your system, you should know if the sensor has any special requirements. So signals, when we speak in terms of data acquisition, are most often some sort of time-varying voltage or current carrying information about some physical phenomenon. And we have to keep in mind that not all signals are measured in the same manner. So first, we need to categorize them depending on whether the signal is analog or digital. That's the most basic categorization. And after we categorize the signal, we need to decide which type of information we want to obtain from the signal. The possible types of information that we can extract are state, rate, level, shape, and frequency, etc., as is shown on the picture on this slide. And going a little bit deeper into the categorization, I would like to say something about analog signals. Analog signals, unlike digital signals, can be at any voltage level with respect to time. And because an analog signal can be at any state at any time, the physical aspects we want to measure here differ from those of a digital signal. And for example, in analog signals, we can measure the level, the shape, or the frequency of the signal. So measuring the level of an analog signal is similar to measuring the state of a digital signal. The difference is that an analog signal can be at any voltage level, but a digital signal is either at a low or a high voltage signal. Then measuring the shape of the signal is often important because analog signals can be at any state with respect to time. So, for example, a sine wave has a different shape than a sawtooth wave. And measuring the shape of a signal can lead to analysis of other aspects of the signal, such as peak values, slope, or integration. And finally, measuring the frequency of an analog signal is similar to measuring the rate of a digital signal. However, now, we cannot directly measure the frequency of an analog signal because we need to perform software analysis on the signal first to extract the information about the frequency, which is usually done using a Fourier transform. And so, in order to acquire these signals and have them processed by a computer, we first need to convert them to a digital form. Um, this is done by taking a representation of the analog signal as a finite set of values in the independent and the dependent variable, where the independent is most often time or space, and the dependent is most often the amplitude. Um, and converting an analog signal into its digital representation is done by using an analog to digital or AD converter. In the picture shown on the slide, we can see an analog signal on the left and its corresponding sampled version or converted into digital form. And we can see that the sampling interval is delta t, or the samples. Each sample is defined at discrete equidistant intervals of time, and it's clear to see that we can get a much more accurate representation of any given analog signal if we use a larger sampling rate or a smaller time interval. But I won't be getting into so much detail about signal sampling in this presentation. So going on to the next slide, we have digital signals. Digital signals have only two possible states: on or logic high, or off logic low. And there's mostly only two aspects of a digital signal that we can measure, and those are the state and the rate. So the state is any digital signal only has two possible states, on or off. So that's one of the aspects of a digital signal that we can measure, whether the state is on or off. And we can also measure the rate. By this, I mean that digital signal changes state with respect to time. So we can measure the rate of how the digital signal changes the states over time. So most often you cannot always connect the signal directly to data acquisition device. And it's probably necessary to alter the signal to make it suitable for a DAQ device to measure. That's where signal conditioning comes into play. And signal conditioning is actually the process of measuring and manipulating signals in order to improve their accuracy, isolation, filtering, and so on. Uh, Signal conditioning is not always required, but most of the time we do need to apply some sort of signal conditioning during the data acquisition. So, as I said, the purpose of the signal conditioning is to take a signal that's difficult for the DAQ device to measure and alter it in order to make it easier to measure. Many sensors need some sort of external hardware to perform their job. For example, RTDs, or resistance temperature detectors, need an excitation current, and strain gauges need a Wheatstone bridge. Um, Also, to measure signals from sensors, the signals must be converted into a form which the data acquisition device can accept. For example, the output voltage of most thermocouples is rather small and susceptible to noise. So most of the time it's necessary to amplify the thermocouple output before it's being digitized. And this amplification is in fact a form of signal conditioning. Sometimes signal conditioning can occur in the sensor itself. For example, some microphones or accelerometers contain built-in amplifier in order to output a more readable signal. Signal conditioning can also occur along the path between the sensor or signal and DAQ hardware. For example, we can place external amplifiers and filters along the path to help reduce the noise. Um, Signal conditioning can also occur within the data acquisition hardware. So going forward, we're going to talk about a little bit about the data acquisition hardware. So a typical data acquisition system has uh, three basic types of hardware: some sort of a terminal block, a cable, and a data acquisition device, as shown in the figure on this slide. Um, so after converting a physical phenomenon into a measurable signal, the signal needs to be acquired. So in order to acquire a signal, first we have, as I said, the terminal block, which provides a place to connect the signals, and it consists of screw terminals or spring terminals or BNC connectors for connecting the signals, and a connector for attaching a cable to connect the terminal block to a data acquisition device. So the data acquisition devices usually have four standard input output elements, which are the analog input, analog output, digital input and output, and counters, as well as all the necessary circuitry for each of these inputs or outputs. The data acquisition device houses the um, analog to digital converter. It has most of them have an onboard clock, and so they handle the acquisition and the transfer of the data to the software located on a computer. And the transfer is done through a variety of different bus structures. So any given DAC device can have different type of interface for communication with the computer. This can be either a PCI, PCI Express, PXI, PXI Express, USB, Ethernet interface, or wireless, etc. So those are some of the common interfaces for communication with the computer. And finally, we have the real-time system integration bus, which allows for synchronization of multiple data acquisition devices, which are being controlled by the same software. For example, if we want two data acquisition devices to acquire an analog signal at the same rate, the real-time system integration bus is the means of synchronizing the clocks of those two devices. We arrive to the final component of a complete data acquisition system, which is the software. The data acquisition software is located on a computer, as I mentioned before, which receives the raw data through the DAQ device, and the application that you write presents and manipulates the raw data in a form that you can understand. The software also controls the data acquisition system by controlling the DAC device and specifying when and from which channels to acquire data. The DAC software thus acts as a single programming interface for programming the analog input, output, digital input and output, and counters or timers on hundreds of multifunction data acquisition hardware devices. Typically, data acquisition software includes drivers and application software. Drivers are unique to the device or type of device and include the set of commands the device accepts. The application software, such as LabVIEW, which we will be using in the further part of this presentation, sends the driver's commands, such as acquire, and returns a reading. The application software also displays and analyzes the acquired data. So, National Instruments measurement devices include the NI-DAQ MX driver software, which is a collection of virtual instruments or functions used in LabVIEW that are used to configure, acquire data from, and send data to the measurement devices. The NI-DAQ MX software is used to communicate with National Instruments DAQ devices, and it provides a user interface and a set of tools for programming and configuring your data acquisition device. So now we're going to take a close look at the NI-DAQ MX virtual instruments. On this slide here, we have the DAQ MX tools palette, which is a palette for LabVIEW that includes all the necessary functions for communication with National Instruments hardware. So first of all, we have these two constants, the first one being the task name constant, which lists all the tasks we have created and saved. Next, we have the channel constant, which lists all the virtual channels we have created and saved. And the channels are actually the link between the software and each input terminal on the data acquisition device, whether that is an analog input or an analog output terminal, or a digital input or output terminal. We can select any one of those using this channel constant, global channel constant. So next we have the VIs, which are the virtual instruments and the main functions that we're going to use when we build our applications. So first we have the create virtual channel VI, which creates a virtual channel or a set of virtual channels and adds them to a task. The instances of this VI correspond to the input-output type of the channel, such as analog input, digital output, or counter output, for example. The measurements or generation to perform, such as temperature measurement, voltage generation, or even counting, and in some cases the sensor to use, such as a thermocouple or RTD for temperature measurements. Um, and next we have the DAQ MX read VI, which is used to read samples from the tasks or channels that we specify, and the instances of this VI specify what format of samples to return, whether to read a single sample or multiple samples at once, and whether to read from one or multiple channels. Next, we have the DAQ MX write VI, which writes samples to the task or the channel that we specify, and the instances of this VI specify the format of the samples to write, whether to write one or multiple samples, and whether to write to one or multiple channels. So these two functions are actually the base of any DAQ software that we're going to write, and are used for reading or acquiring or writing or generating uh, any sort of signal that we're going to need to do. So next we have the wait until done VI, which is a VI that writes sorry which is a VI that waits for the measurement or generation to complete. And we use this VI to ensure that the specified operation is complete before the task is stopped. Then we have another VI that we're going to use quite often, and that is the timing VI, which configures the numbers of samples we want to acquire or generate and creates a buffer when necessary. The instances of this VI correspond to the type of timing and source that we want to use on our task. Next, we have the triggering VI, which configures triggering for the task at hand, and the instances of this VI correspond to the trigger and the trigger type we want to configure. Next, we have the start and stop task VI, which the start task VI transitions the task to the running state to begin the measurement or generation. And using this VI is required for some applications and is optional for others. Um, and the stop task VI stops any given task and returns it to the state the task was in before we use the start task VI. And finally, we have the clear task VI, which clears the task. And before clearing it, this VI stops the task if necessary and releases any resources reserved by the task. And a task cannot be used after it has been cleared, and unless it is recreated again. And these other functions are the third row of functions are property nodes, which we won't be discussing or using in this presentation. And on the final row we have an Express VI DAQ assistant, which is used for conducting very simplified, simple measurements. Um, if we don't have enough time to write complete code by ourselves. And these other icons here represent subpalettes, the real-time VIs that are found in the real-time subpalette are used to configure and perform real-time operations. The DAC-MX device configuration subpalette is used for hardware-specific configuration and control. The advanced task options subpalette is used for advanced configuration and control of the tasks that we create, and the advanced palette and the VIs that are in it are used to access some advanced and miscellaneous features of the NI-DAC MX. So now I just want to go over the waveform data type briefly, because I already mentioned that this presentation is intended for students that have previous experience in LabVIEW. I'm sure that most of you already know what the waveform data type is, but just as a short reminder, the waveform data type is a cluster that consists of four different elements. First of all, we have Y, that's a one-dimensional array of numeric data points, which can be a single point or a waveform depending on the operation. And the representation of the 1D array is double. Next, we have the T0, which is a scalar value that represents the time according to the system clock when the first point in the Y array was acquired. And this element is also called the initial time or the timestamp. And then we have the delta T, which is a scalar value that represents the time between all of the data points in the Y array. So all of these data points are acquired at equidistant time intervals at the same time interval, which equals delta t. And the attributes is a string that allows you to bundle other information along with the waveforms, such as the device number or channel number from where the data was acquired. So mainly the benefits of using the waveform data type are the presence of T0, because before this data type existed, you couldn't determine when the data was acquired. So the waveform data type automatically returns the time of day and the date in this element, which gives you a real-world acquisition time for the data. And it also enables easier plotting of the signals, so easier graphing of the signals, as well as easier multiple plot graphing in LabVIEW. Okay, so now we're going forward and we're going to start first with the analog input acquisition techniques. So first of all, I just want to have a close look at how the DAC-MX read VI is used to read analog signals. So DAC-MX read VI, located on the data acquisition palette, reads samples from the tasks or channels that we specify, and the instances of this VI specify what format of samples to return, whether to read a single or multiple samples at once, and whether to read from one or multiple channels. So on the DAC-MX palette, we have the read function, and I'm just going to place it here on the block diagram. And what I did is I created a control to specify the input channel, and using the drop-down menu, I I have the option to select which type of data I want to read, whether that's a single channel or a multiple channels, and whether to read single samples or multiple samples at once, and in which data form uh, I want them outputted into my lab. For this example, I chose the waveform data type. So here we have already the single samples software timed acquisition, which is a really a basic acquisition technique, but we're going to start off with this one right now. So you can see the process of creating this block diagram. I'm opening the tools palette here, and first I'm going to use the create channel VI placed on the block diagram and select analog input voltage. Next, I'm creating a control for selection of the physical channel that corresponds to the input terminal block on my data acquisition device. And next, I'm using the start task function. So now um, I'm going to go ahead and create a while loop here in which I'm going to place the read uh, analog read virtual instruments, and for this example we're going to read a scalar value, or just um, just a decimal number, a double. And this while loop um, allows allows the program to repeat the measurement at software timed intervals. That's why I use the wait until next millisecond multiple function here, and I'm going to set it to 100 milliseconds. So what this code is going to do, it's going to acquire samples at 100 millisecond intervals from the data acquisition device and output them on this indicator titled data. And this is going to continue until we stop the application using the stop button that I just created. And finally, we need to clear the task and use a. I'm going to place a simple error handler VI here to handle any errors that might occur in the program. So that's the block diagram of the software timed acquisition. Um, and we're going to go on now to the finite buffered acquisition right now, which is a technique that we want to use in order to prevent timing issues, because the LabVIEW software runs on an operating system, most often on Windows, which does have some issues when considering really precise timing, especially if we're talking about periods less than a couple of milliseconds. And in order to have really precise measurements carried out here, we can use this technique, which allows us to acquire a certain amount of samples at equidistant time intervals, controlled by the hardware clock of the device, rather than having the timing being controlled from the software. So the DAQ MX timing VI will configure the sample rate, the number of samples to acquire or generate, and will create a buffer when necessary. So next, after that, we want to start the acquisition, start the readout, and when we're done, when the DAQ device has returned all the samples that we have wanted to read, the task stops and the application ends. So Here we have this technique shown on this slide. So the process is fairly similar to what we did last time, except for we have the insertion of the timing VI into the code as well. So once again, um, create channel VI. We create a control to specify the physical channel on the data acquisition device, and yeah, here we can set the minimum and maximum value we want the the device to acquire. And now we place the timing VI on the block diagram. So we are going to configure it in sample clock. Um, this means that it will use the hardware clock of the device. And we want to choose uh, finite samples in the sampling mode input, and here we can also create a control regarding the number of samples per channel we want to acquire, and the final control that we create controls the sampling rate of the acquisition. So after we connect the task in of the create channel to the task in of the sample clock, we add the start task VI, and then comes the um, read VI. So because we are acquiring multiple samples here, we need to go a single channel but multiple samples, and I'm going to select a 1D array of doubles. So all the measured points will be returned in this array on the output of this virtual instrument. That's the indicator. So after this, the task will stop automatically after the read out will stop automatically after the final sample has been read. So all that's left is to clear the task and add a error handler to the program here. So now we're going to continue with the continuous buffered acquisition. And the main difference between a finite buffered acquisition and a continuous buffered acquisition is the number of points that we acquire. With a finite buffered acquisition, we can acquire a set number of points, whereas with continuous buffered acquisition, we can acquire data indefinitely. So on this flow chart, we can see the difference between these two approaches. And as you can see, after we configure the device and start the acquisition, we go into a loop that constantly checks if we want to keep acquiring data and return it from the buffer. And until we choose to stop the task, it will keep acquiring this data constantly. After we choose to end the task, the stop task VI is called and it stops the acquisition, and that will end the program. So the programming part is again similar to what we did last time. We have the create channel VI. We select the physical channel via that control, and we place the timing VI again in sample clock mode of operation. We only this time for for the for the sampling mode, we choose continuous samples instead of finite samples. And after this, we use the start task VI, and now we're going to place the read VI in a while loop, through which we will control for how long we want the acquisition to run for. Again, we want to select single channel but multiple samples. And let's go with a waveform this time, for example. This is the indicator where the measured data will be output, and this is the number of samples per channel if you want to specify that as well. Now we're just going to add a simple stop button to help us control for how long we want the acquisition to run. And after that's finished, we add the clear task VI at the end of the while loop and the simple error handler right there. We can clean up this diagram to make it look prettier, and that's the continuous buffered acquisition technique. Okay, so those were the three essential analog input acquisition techniques. So now we're going forward with the analog output acquisition techniques, or the analog generation techniques. So let's go over using the analog write VI. Essentially, it's pretty much the same as using the analog read VI, with the sole difference that instead of the function having an output, it has an input where we need to wire the data we want to write to the physical channel, or the data we want to generate. So we need to select what sort of data we want to output, whether that's single channel or multiple channel, single sample, multiple sample, and simply wire the data to the data input as I just showed you. So the single sample generation is basically the same as the single sample acquisition that we covered in the previous topic of the video, so I'm not going to show you the block diagram of the single sample generation acquisition technique. Instead, I wanted to talk a little bit about the difference between software and hardware timing. So when we use software timing, the rate at which samples are generated is determined by the software application and the operating system, and not the DAQ device. And because the generation is entirely dependent on the operating system's resources, um, any interruption in the system can possibly affect the generation. That's why the hardware-timed generation uses a TTL signal, such as a clock on the data acquisition device, to control the rate of generation. Hardware-timed generation can run at a much faster rate than a software-timed generation and maintain a higher value of accuracy. We need to know that not all devices support hardware timing. Um, the timing VI has several modes for setting the timing for an analog output generation. If we select the sample clock instance of the timing VI, we are telling the DAQ MX to use the sample clock from the DAQ device to control the generation. Um, for software time generation, the sample timing type should be set to on demand. And if we want to use waveform data for the timing of the generation, we want to use the use waveform instance. And this instance uses the delta t component of the waveform input to determine the sample clock rate, where delta t is the time in seconds between each sample. Now going on to the finite buffer generation. If we want to generate multiple analog output samples, we need to configure the pull-down menu of the DAQ MX Write VI for multiple samples. We use a multiple sample generation if we want to generate a time-varying signal, such as an AC sine wave, for example. Multiple point generation is also known as buffered analog output, which can either be finite or continuous. However, both buffering methods involve the following two main steps. First, writing samples into the buffer. The points are taken from LabVIEW and placed in an intermediate memory buffer before they are sent to the device. So a buffer generation is similar to sending an entire email at once instead of sending it one word at a time. That's the analogy. And then transferring samples from the buffer to the DAC device. The rate at which the samples are transferred depends on the timing that is specified. As with single sample generation, either a software or hardware timed generation can be used. So this is the flow chart of the finite buffered generation. So we configure the clock of the device, then we write the data into the buffer, and after we start the generation, um, the um, the data will be outputted, and using the wait until generation completes VI, the application will wait until the final sample has been generated to stop the task and um, and the execution of the program. So um, there are two ways. I'm going to show you two ways of using the sample clock, of using the timing VI here. First, we're going to be using the sample clock. So this is a known procedure. We create the channel. This time we want to select analog output voltage, create a control for the physical channel, and um, set the timing VI in the sample clock method. We create a control to control the sampling rate, and next we choose the sampling mode as finite samples. So because we want to generate a certain amount of data, which is multiple samples, we're using an array here. So the number of samples per channel is going to be the array size. And next we um, we add the write function. We have to select multiple samples, and the type of data is one-dimensional array of doubles. So next we add the start task VI and the wait until done VI, which will wait until all the samples have been generated and then proceed to stopping and clearing the task. Okay, so sticking with the same example, I just wanted to show you the different use of the timing VI. So here we want to use waveform in order to control the timing of the generation. So we're going to remove this array control, and we're going to remove the sampling rate control as well. And now we're going to set the timing VI in the use waveform mode. And we also need to change the mode of the write function. So instead of 1D double, we choose analog waveform. And on the data input of the function, we are going to wire waveform control, which will represent the data that we want to generate. And the same waveform control is going to be wired to the waveform input of this instance of the timing VI. We can go ahead and set the auto start of the write function to true if we want um, uh, the generation to begin automatically. So now we're going forward to the continuous buffer generation, and the main difference between a finite buffer generation and a continuous buffer generation is the number of points that are generated. So in a finite buffer generation, we generate the data in the buffer a finite number of times, whereas in a continuous buffer generation, the data can be generated indefinitely, as shown on this flow chart. So until a certain condition is met, um, which in our example will be the pressing of a stop button or the occurrence of an error, we can virtually generate infinite amounts of data. And here is the continuous buffered generation technique. So we create a physical channel for analog output voltage. We create the physical channel control, and we place the timing VI in the sample clock. Mode, we're going to create a control for the sampling rate, and we're going to create a constant for the sample mode, which we're going to set to continuous samples. This is very similar to the continuous buffered acquisition, and the number of samples per channel to generate. And next we have the analog write function. So we're going to need multiple samples, 1D array of doubles. We're going to create the data array control. That's the data we want to output. And we're going to place the start task VI, as we've already seen. And the final step of this this technique is adding a while loop in which we are going to place is task done VI. That's found in the task config subpalette, and there it is. That's the DAQ is task done VI. And on the output of the while loop, we're going to place the clear task VI. This is the we're adding the stop button now. That's to control for how long I want the data to be generated, and of course the clear task to clear all the resources the task has saved up, and the error handler VI. So that's the continuous buffer generation technique. Now we're going forward with the final topic of this presentation, which is the digital input and output acquisition techniques. So first, just a brief overview of the digital input-output signals terminology in LabVIEW. First, I just want to mention that for most data acquisition devices, the digital lines accept and generate TTL compatible signals. TTL signal, as shown on the picture on this slide, has two states. That's logic low and logic high, where logic low signals are signals between 0 and 0.8 volts, whereas logic high signals are between 2 and 5 volts, where signals between plus 0.8 and 2 volts are indeterminate. Following are some of the common terms used with digital input-output operations. Of course, bit is the smallest unit of data used in a digital operation. Bits are binary, so they can either be a 1 or a 0. Next is a byte, which is a binary number consisting of 8 related bits of data. Bytes are also used to denote the amount of memory required to store 1 byte of data. Then we have lines. A line is an individual signal in a digital port. So the difference between a bit and a line is that the bit refers to the actual data transferred, and the line refers to the hardware that the bit is transferred on. However, they are fairly interchangeable terms. For example, an 8-bit port is the same as a port with 8 lines. So next we have port. A port is a collection of digital lines, and usually the lines are grouped into an 8-bit port. Typical multifunction DAQ devices have multiple 8-bit ports, where each of these ports contain 8 lines of bidirectional digital input-output signal. Then the port width is the number of lines in a port. For example, some DAQ devices have 3 ports, each containing 8 digital lines. Therefore, the port width is 8. And the mask determines if a digital line is ignored. For example, if you write to a port, but you do not want to write to all the lines, you can set a mask to ignore the lines you do not want to write to. The digital channel data formats deal with the type of the digital data that is read or written. And you can choose which data format to use when using the DAQ-MX read and write VI. So the line format represents each line with a channel as a single Boolean value. The states of the data are limited to true or false, and line formats are only provided for single sample reads and writes. And the next format is the port format, which matches the native format of digital devices that can represent only 2 digital states and organize individual lines into collection known as ports. So just a brief introduction to using the DAQ-MX digital read and write functions. Um, just as when using these functions to perform analog operations, we have the option to select digital read or write. So here we have the digital read function, and we can choose again between single or multiple channels and single or multiple samples given in the following formats shown on the presentation. So the usage is fairly simple and is the same as we've seen before. The DAQ MX read VI reads samples to the task or the channels that we specify, whereas the DAQ MX read VI reads the samples from the task or the channel. The instances of these VIs will specify the format of the samples to write, whether to write one or multiple samples, and whether to write to one or multiple channels. By default, the auto start input of the DAC MX write VI is true when writing single samples, and it's set to false by default when writing multiple samples, if we leave it unwired. So now we're going to have a look at the digital read and write VIs and how to use them. These are in fact the same virtual instruments that we use for digital and for analog generation um, and input. We just have to select the corresponding um, instance of the instrument. So we need a digital um, input or output of, I mean, the read function is the one that handles the so now we'll just a close look at how we use the DAC MX digital read and write VIs. So these are the same VIs we use to read and write analog signals. The DAC MX read VI reads samples from the task or the channel that we specify, whereas the DAC MX write VI writes samples to the task or the channel that we specify. And this instances of these VIs will specify the format of the samples to write, whether to write one or multiple samples, and whether to write to one or multiple channels. So all we need to do is select the correct instance for the task we want to accomplish. Um, Here we have the write function. We need to select digital output, single channel, for example, single sample, and one that's just one Boolean value, and connect the data we want to write to the data input of the function. So by default, the auto start input of the DAC MX write VI is true when writing single samples, and is false when writing multiple samples. This is when we leave that input unwired. Now we move on to the hardware-timed digital input and output acquisition techniques. So we're going to be looking at an example of hardware-timed continuous generation. So some DAC devices have a dedicated onboard sample clock for digital input and output, and you can program the hardware-timed acquisitions and generations just in the same way that we programmed the hardware-timed analog acquisitions and generations in the previous topics of this presentation by using the DAC-MX timing um, VI. So here we use the onboard digital sample clock. The procedure is very well established by now, I'm sure. So we create the physical channel. We need to select digital output. And next we we're going to set up uh, the timing VI to use the onboard digital uh, clock. We're going to create a control here for the sampling rate, constant for the sampling mode. We said we would be using continuous samples. And next comes the write, uh, the DAQ write function. So we need to select the appropriate instance. We need digital, single channel, multiple samples, um, and we're going to go with uh, this 1D array of um, um, 32 unsigned integer, 32. Here we need to create the control for the data we want to generate. Next comes the start task VI. And as we did in some of the previous examples, we will place the is task done VI in this while loop. And we're going to check for the condition. The condition is again going to be a stop button, which will stop the generation when we want it to. And we're going to check this every 100 milliseconds. That's why we are going to add this wait until next millisecond multiple function here and wire 100 milliseconds to it. And I'm just adding the stop button now. So this generation stops when we click the stop button or when an error occurs in the program. And after that, we just need to um, add the clear task VI and an error handler VI as well. So because some DAQ devices do not have a dedicated onboard sample clock for digital input-output, but do support correlated digital input-output. This means that these devices can use a different clock, most often the A analog input or analog output sample clock, or an external clock for hardware-timed acquisitions and generations. All we need to do is specify which clock to use with the source input of the DAQ MX timing VI, and I'm going to keep with the same example, and I'm just going to add this control to the source input. So there's the source input, and we need to add another control which will specify which will allow us to specify which clock to use as a source. So we can use hardware time digital generation even if the device itself does not have an onboard sample clock for digital inputs or outputs. So that was my presentation on the subject of data acquisition techniques using LabVIEW. I hope you found it useful, and I hope you learned something new, and that you will find these techniques useful in your future um, uh, careers and when using LabVIEW as well. So that's about it. I would like to just thank you for your time and for your attention. My name is once again Bodan Vilkovsky, and I'm wishing you all the best.